Hello, Professor Dieterlen. Nice to meet you. Is it okay you take the two first and I will take the last one? I cannot hear you.
Okay. Yeah, it's okay.
That's fine.
Yeah.
You have the toughest job and I'll just relax. So I will disappear again, but I'll listen, but I will mute my computer and mute my video.
Yes.
So maybe I have a question. I don't know. Time will show.
Good afternoon. 2 p.m. we start.
Thank you, Claudia. So, hello, everybody. I suggest that we start with the first speaker. And the first speaker is Peter Naglič, if I pronounce correctly, from University of Ljubljana in Slovenia, sorry. And I give you the connection, not the floor, but the connection. And you can share your screen.
Yeah, thank you very much. Let me just share the screen. Okay, let's see. Okay. Okay, do you see the presentation?
Yeah, okay. It's okay.
Okay. So yeah, thank you very much for giving me this opportunity to talk at the conference. My name is Peter Naglič, and I will present digital holographic microscopy in a reflection mode for observation of liquid crystals on various substrates. So in the beginning, I will present motivation and a short introduction to digital holography. Then I will present how we numerically process acquired digital holograms. Then I'll present our experimental setup that we are using for digital holographic microscopy in reflection mode. Then in the second part, I will make a short introduction to liquid crystals, show some preliminary experiments that we did using 5Cb liquid crystal, and then conclude with some future work. So the motivation for using digital holographic microscopy would be in the fact that it allows reconstruction of the entire object scattered wave field, and this with some additional regularizations such as multi-angle illumination allows volumetric reconstruction of the entire director field of liquid crystal, and in a label-free fashion, which is actually really nice. And this is quite a hot topic, and it has been recently done in transmission mode by two groups and we see the results here on the this image. So conventionally, liquid crystals are observed using conventional polarized light microscopy, and this usually gives just a 2D projection, and it's good to have information that is also out of the plane positions of the molecules, of the liquid crystal molecules. Although now there are many other options to also have quantitative methods on top of just the conventional polarized light microscopy. So digital holography consists of recording an interference pattern that we know as a hologram on a digital sensor between an object wave and a reference wave. The object wave interacts with the sample and it's interfered with the reference wave. Here, mathematically, this can be described in the following way, where when we expand this, we obtain two intensity terms and then two interference terms corresponding to twin images of an object, and we are interested in the amplitude and phase of an object. Now, if I go into a little bit more details, so if we don't have any object in our sample plane and we interfere the object and reference waves at an angle, we just obtain straight fringes. But if we introduce an object, we obtain this phase shift that bends the fringes, and we can analyze this numerically by doing a Fourier transform, where we obtain three spectral islands. The central one are the constant intensities that I mentioned earlier, and then the two islands next to it are basically twin images of the object. We can do spectrum filtering in the Fourier space and then do an inverse Fourier transformation to obtain the amplitude and phase of our object. And the phase delay, the phase shift that an object introduces is many times more than just minus and plus pi. So we have to use also phase unwrapping algorithms to get the unwrapped phase. The experimental setup that we are using in our laboratory looks something like this. So it's based on a relay of tube lens and microscope objective that comprises an ordinary optical microscope, but we input the laser beam at one side and split it into an object beam and reference beam. Object beam interacts with the sample and is then interfered with the reference wave, reference beam at an angle, although it's not visible here. And we also use broadband light source to do conventional polarized light microscopy at the same time. So the first thing that we can try with our system is just to see the topography of a standard USAF target, and these targets are usually nice because they have a thin layer of chromium deposited on a glass slide, and this thin layer is about of a thickness of around 100 nanometers, and the height is connected directly to the quantitative phase that we record. And if we do the reconstruction, we can get this type of a topography profile. And yeah, if we do a cross section, we can see that this profile is yeah, exactly what we would expect, so around 100 nanometers. So the vertical resolution in this case would be well below 100 nanometers, but lateral resolution is still limited as that of a conventional optical microscope. To be precise, it's even a little bit worse because we are filtering in the Fourier space, so we are kind of losing also maybe some frequencies due to this process. Okay, So now the introduction to liquid crystals. So we are. Sorry?
Just noise. Continue, please.
Yeah, okay. So we are used to substances being in three phases: solid phase, liquid phase, and vapor phase, let's say. But liquid crystals are characterized by additional condensed states phases than just solid and liquid. And these intermediate phases are termed mesophases. And here we have a conventional schematic of a 5 Cb liquid crystal that has these elongated molecules, and it actually has two phase transitions due to the temperature. The first one occurs at about 24 degrees, and it goes from a molecular crystal, so from a solid to a nematic mesophase. And in a nematic mesophase, because the molecules are elongated, they tend to orientate along a preferred axis that we call a director. They actually fluctuate around this one, and in this case, the positional order is broken, but the orientational order is still very high and long-ranging. And then if we increase the temperature even more, we get an isotropic liquid that we are also quite used to. In addition to this orientational order, what's also very important with liquid crystals is surface anchoring. So in the most basic sense, we have planar and homeotropic surface anchoring, but of course we have also intermediate ones. So for example, tilts of liquid crystals. And then since the liquid crystals, so the liquid crystal molecules tend to align in parallel, there are certain locations where the orientational order is broken, and this is what we call topological defects. And here are 3 examples of these defects you can actually observe. Okay, so in the isotropic case that we had before, the phase could be really easily related to height, but and from there to topography. But in case of birefringent materials, the interpretation of the reconstructed phase is a little bit more complicated and depends on the polarized light configuration. So it depends on the input and output configuration. So for example, for cross-polarized polarization, the phase, if we do the Jones calculus, for a linear retarder, for example, for a tilted linear retarder, rotated linear retarder, we get this phase. So it depends only on the phase delays of the linear retarder, but not actually on the rotation. And if we have a liquid crystal that has a director field in the XY plane, this equation translates to that it depends only on the wavelength of light, the extraordinary and ordinary refractive indices, and the thickness of this liquid crystal that we are observing. So the this quantitative phase that we obtain with digital holographic microscopy then depends on these parameters, basically. But since in our case we are observing these surfaces, silicon substrates on which we put the liquid crystal, so silicon substrate actually induces planar anchoring, but the liquid crystal is basically exposed to air at the top surface, and air actually so this top surface actually prefers homeotropic anchoring, so perpendicular or zero zenithal angle. But since we are dealing with very thin layers of liquid crystals, it's not necessary that the liquid crystal molecules would orientate at an angle, completely perpendicularly, but they could be tilted. And so the quantitative phase that we obtain with digital holographic microscopy now depends on the total optical path that now depends on the orientation of the molecules along the z-axis, and this orientation can be modeled with a linear profile of the angle. So it goes from 90 degrees, so pi over 2, to some arbitrary angle that can be either completely homeotropic, which would be 0, or to some specific angle. And so the quantitative phase now depends not only on the refractive indices, but now also on this surface anchoring angle that we, in principle, don't know. And but our goal, for example, is here to just determine the topography of the liquid crystal. So we would just like to determine the thickness of the liquid crystal. And what we can do as a first try is to actually just say, okay, what if we replace this integral here with just extraordinary refractive index and see what kind of an error we make for different this top surface anchoring angles. And we can see if the angle here is so 0, that means that we have homeotropic anchoring. The maximal error that we make to the thickness or the height is actually only minus 3%. So we make a 3% underestimation of height if we do this approximation. So we can actually proceed as a first, as a crude approximation, we can proceed with just replacing this term with extraordinary refractive index. And as a sanity check, we can do thin film interference. We can observe thin film interference of the liquid crystal, obtain the thickness, and also using a Berek compensator with which we match the retardance of liquid crystal to measure the, we can then use this measurement of the retardance and the thickness to actually obtain the top surface anchoring angle and see what kind of an error we introduced in this step. So here is the first example, and in this case we put the liquid crystal just next to this microstructures, so just on a smooth silicon surface, and we can see this Schlieren-like texture. And if we observe the Michel-Levy chart, we can see that the thickness here is definitely below 500 nanometers. If we observe the thin film interference in the parallel polarization, we observe in this yellow region that the thickness is about, this color is about yellow, so it's about 180 nanometers. And using the Berek compensator, which we can see the measurement being performed here, we can get a surface anchoring angle of around 34 degrees. So that would mean that we are doing around 2% error for using digital holographic microscopy to determine the thickness of our liquid crystal. So here on the right side, we see the reconstructed face, and actually this is already converted to height or the topography of the liquid crystal. And by observing the color chart, we can actually see that it matches quite well the thin film interference. And then we also get this amplitude image. So basically more information with this modality. So yeah, this is a rendering. And now we can do the same experiment, but basically pouring the liquid crystal onto this silicon substrate with such pillars that are 10 micrometers in diameter and separated by 30 micrometers. And in this case, since, for example, if we place a liquid crystal on a smooth silicon surface, we get this random textures. But for studying, it's really good to have a controlled approach in creating and positioning topological defects. And with this substrate, we can achieve exactly that. So in this case, for example, that we see here, we have +1 and -1 topological defects. So basically we have defects between the pillars. Here these are positive, they have a positive 1 winding number, and then the pillars themselves act as a -1 topological defects. And here we can see the interference, thin film interference image that shows that the liquid crystal has a topography with saddles between 2 pillars and minima between 4 pillars. And so if we do the same analysis again, we can, so using again thin film interference and Barak compensator, we can see that the surface anchoring in this case would be 45 degrees. So again, if we do, if we convert phase to height, we won't do a lot of, of an error. So here I'm just showing first the wrapped phase so that we can see that it has quite a complicated structure, but we can still see the isohips and this saddles, and we can do the phase unwrapping, although in this case it doesn't work as best as possible. This part here is deliberately saturated because I wanted to point out especially these parts here that show that this type of a topography of a liquid crystal. And again, we have an amplitude image here. Okay, and finally, I would like to show a third example, which is actually really useful when using digital holographic microscopy, and that is for observation of dynamical processes. So this image here shows a phase transition of a 5Cb liquid crystal from isotropic to a nematic state. So first we have just a black, just empty image in cross polarization, and then when the this phase transition happens, we get these declination lines, but you can see they are defocused, and this happens because we are cooling the sample, and due to some thermal effects, the heating stage might shrink, and so it would become defocused. And we would like to observe this phenomena in focus. And since digital holographic microscopy offers reconstruction of the whole wave field, we can actually propagate it then numerically. So after we did the experiment, and we can see now the declination lines getting refocused. So this is really useful for dynamical processes. Okay, so yeah, what I presented here is early work, and results are not interpreted in as much in detail as I would like. So in the future, we would like to investigate optimal input-output polarizations, configurations to get as much information out as possible of this system. We plan to improve the phase unwrapping algorithms using machine learning, which is actually quite a hot topic at the moment as well. Then to interpret our quantitative phase that we obtain with digital holography, we need to utilize more rigorous models for light propagation, such as through B-refringent materials, such as liquid crystals. One such tool is, for example, Naglič, which is an open source tool. And then, finally, our goal is to establish a routine experimental tool for investigation of liquid crystals on various surfaces that we are investigating in our lab. So with this, I would like to thank you for your attention.
Thank you for this presentation and your nice results, and discussion is open. There are any question or
I have one question.
Yes, Tim.
Thank you for a very good, it was very impressive, your presentation. I have one question, that is, what is the update rate? How fast can you make measurements? I'm not talking real time, but you take a lot of readings and then afterwards you process them. What's the update rate?
So, so in principle, if we would consider the so the acquisition and processing, then it depends on the mostly on the processing phase. So doing the Fourier transformations and then getting the quantitative measurements. And this can be done on graphical processing units, but this I would assume would be the bottleneck. But we can do the processing offline. So after we already did the experiment. And in this case, if we just acquire the images, it's basically a snapshot method. So it depends on the frame rate of our camera. So we can use actually fast cameras to record the holograms and then do the processing offline.
Thank you. Thank you.
Thank you.
Okay. Thank you. Other question?
Hello.
Yes.
Thank you for nice presentation. One question about phase unwrapping. It seems from presentation that it always counted like profile increasing. So means each step of the phase leads to increasing of profile. Is it true or it is just impression from presentation?
So maybe... I didn't...
So means profile of the real object can go down and go up. Unwrapping, it seems like it always go up only. So I'm curious if it's just impression of the presentation or it's real disadvantage of this algorithm.
So it can occur actually. So yeah, it can go down as well. So we had situations where certain parts went up and certain parts went down, and it depends on the algorithm. And also, yeah, because we expect in certain cases in which direction it should go, we then do how should I say, some educated guess in which direction it should go. So yeah, that's also considered.
Yes, thank you. So it's like good candidate for probably artificial intelligence use, right here?
Yes, exactly, because there we should input some information because it's also there, and this is ideal case for artificial intelligence. Yeah.
Yes, thank you.
Thank you.
Yes, thank you. So I see that the timing is running, and I suggest that we move to the next speaker. Thank you, Peter. And so the next speaker is Igor Mokhun from our host university in Chernivtsi. So Igor, where are you?
Thank you.
And you can share your screen. Thank you.
Just a moment.
Yeah.
I have some technical problems, but I think that can you see my presentation?
It's coming. Yes. Yes.
Okay.
But actually, it's not in the presentation mode. It's
okay.
Yeah, it's okay. No, it's okay.
This is the title of my report. First of all, it so happens that I am one of the researchers who pays close attention to the instantaneous or temporal realization of field parameters, at least when polychromatic fields or superposition of limited number of monochromatic waves with different frequencies are considered. However, as it is known in optics, as a rule, averaged wave parameters are observed. This is a traditional optical approach. Therefore, the report presents results obtained specifically for this situation. I know that conclusions drawn from the obtained by us results don't claim any generality, and in fact, there are some estimates regarding the formation of energy flows in polychromatic ways. As to coherent case, it can be stated that the theory of energy flows in optical waves is practically completely developed. See, for example, these articles or a lot of good fundamental and applied papers. What is not done? Very briefly, a more general case, polychromatic waves, was practically not considered. In particular, is not entirely clear how energy flows are formed in polychromatic waves. What is known, in particular, relationships for the averaged by time Poynting vector in the case of paraxial approximation obtained. The resulting Poynting vector is the sum of corresponding spectral components. A similar statement is absolutely true for angular momentum. Obviously, the behavior of energy flow in polychromatic fields must be related to the structure of the analyzed field. In the analysis, we will base on such axiomatic assumptions. The first, each spectral component forms its own distributions of the characteristic of the Poynting vector. Note that such spectral distribution is different to each other at least by space scale. And the second, the resulting transversal component of the vector is formed as simple sum of spectral vectors. Then, indeed, due such statements, one can really expect different behavior of the Poynting vector in the fields with different structures. In this sense, we have identified two boundary cases of the field structures. The first of them, fields of general type, a good example, the speckle fields, and the second, certain fields with central symmetry like Gaussian beam or Vortex 1. For a field of general type, quasi-randomly directed vectors with different modulus are summed at each point of the field. As a result, in field with destroyed coherence, the resulting vectors tends to 0. In another situation is realized for some symmetrical polychromatic beams like Gaussian beams of Vortex or Vortex 1. We will call such beams elementary symmetrical polychromatic beams. For such beams, partial spectral Poynting vector at each point are collinear. Accordingly to this, the modulus of the vector are summed up like in coherent case. Note that such situation is not always realized for beams with central symmetry of wave parameters. As an example, we present the distribution of the Poynting vector for the red and blue components of the chain of vortices. As we can see, at least decrease of the resulting average magnitude of the Poynting vector compared to the coherent case is observed. We will refer to such situation as the formation of ordered polychromatic beams. From the point of view of the formation of the transversal energy flows, such beams occupy an intermediate place between fields of the general type and elementary symmetrical polychromatic beams, because a significant large magnitude of the Poynting vector is preserved. Let us turn our attention to a well-known fact. If a significant angular momentum is formed in the vicinity of a certain point of the field, then the circulation of the pointing vector is observed in this region. At the same time, the analysis of the behavior of the characteristic of the vector does not make it possible to establish what type of angular momentum, orbital or spin, such circulation is consequent of. Due to that, the choice of a specific beam type does not matter for consideration elementary symmetrical polychromatic beams parameters. Therefore, as such beam with some angular momentum, we choose a secularly polarized polychromatic Gaussian beam. The components of the electric fields for such beam may be represented as here. It can be seen from this relation that contribution from the spectral components is governed by normal distribution. Naturally, this is not completely correct due to the fact that the negative frequencies don't exist. Nevertheless, we will assume that spectrum falls off very quickly and the contribution of negative frequencies can be neglected. Then the components of the pointing vector can be written in this form, as it follows from these papers. The Stokes parameter here is the simple sum of the spectral Stokes parameters. Accordingly to this, the components of the pointing vector have this form. From this relation, we can see that pointing vector in our case are absolutely the same as in the coherent situations. Moreover, it is easy to show that for white vortex, we have a similar notation. Conclusion: the magnitude of the transversal component of the pointing vector, the magnitude of the resulting angular momentum in elementary symmetrical polychromatic beams is the same as in coherent case. Now, we will consider what will happen to the components of the pointing vector if such beam symmetry is destroyed. How are we going to break the symmetry? Note that in the coherent case, small physical perturbations along the optical path, as a rule, don't destroy the space structure of distribution of optical parameters, but only lead to some spatial deformation of distribution. At the same time, the base properties of the distributions remain unchanged. In inspection may be the destruction of topological defects, such as vortices with charge greater than unity and other similar situations. This also no decrease in the value, at least mean magnitude, of the transversal component of the pointing vector. Therefore, in our opinion, the main factor that determines changes in the structure of the energy flow of a polychromatic wave is the mutual displacement of singular points, vortices, pointing singularities, etc., in different spectral components. Therefore, as a working model that allow us to identify changes in a polychromatic wave due to the destruction or transformation of symmetry, we have chosen the following. We considered the shift of center singular points of spectral components relatively to the initial positions. Such shift may be regular along one direction transformation of symmetry from axial to axial, from central to axial one, or maybe chaotic. Okay. Note that the process of regular beam transformation can be carried out in such a scheme using two prisms. Or another example, the diffraction of white vortex on the edge of screen it is known for monochromatic vortices. Under such operations, the centers of vortices in the far field shifts relatively to initial positions. Like random shift, we can consider the situation when our polychromatic beams propagates along the path with some random physical perturbation like turbulence. The degree of transformation or destruction of the symmetry we will define by the magnitude of the mean shift of the spectral components. Such estimates were made on the basis of the results of computer simulation of the search of spectral components of the white vortex. The simulation results obtained when the equality of mean shift under random and regular transformation is realized. Here we have the mean shift is about 10%. A, B, and B figure corresponds to the initial fields. C, D is regular shift, and E, F correspond to the random shift. As it is seen from this figure, the field parameters for the regular shift changes little. As to random shift, it can be seen that the deep maximum in the center of beam is practically disappeared, but the circulation of pointing vector near the singular points is observed for both cases. Shift is about 25%. It can be seen that deep minimum for regular shift is disappeared also. And for random shift, we can see that the minimum changes to maximum, but the circulation of the pointing vector is observed for both cases. The shift is about 35%. It can be seen that here we practically don't see minimum, don't see minimum, and for random shift we can state that the behavior of the pointing vector is practically destroyed relatively to initial distributions. And finally, this is regular shift is about which equals to 80% of initial beam width. We can see that even in this case, we can see the circulation of the pointing vector. Thus, the magnitude of the transversal components of the pointing vector remains zero at singular point, even for significant shift of the spectral components. So even a shift of the order of 40% of beam width for any nature of shift, circulation of the transversal components of the pointing vector is observed. However, in the case of random shift, changes of the behavior of the beam characteristics occur much faster than in the transition from central to axial symmetry. For regular shift of centers of the spectral components of the order of 80% of beam width, the modulus of the component is remain about 60% of the initial amplitude. Note that for a field of general type and complete distraction of coherence of a polychromatic waves, the magnitude of the transversal components tends to zero. If we take into account these facts, then we can draw the following general conclusion. The magnitude of the transversal component of the pointing vector only in elementary symmetrical polychromatic beams is the same as in the coherent case. The same is magnitude of the angular momentum. For all other fields, the magnitude of the transversal component of the pointing vector decreases compared to the coherent situations. The smallest increasing is observed for ordered beams. In the process of propagation of elementary symmetrical polychromatic beams, the presence of physical perturbations in the optical path due to the transformation of symmetry or caustic distraction of symmetry, pointing component magnitude decreases. When symmetry is transformed, the magnitude of the transversal component of the pointing vector remains significant. For shift of the spectral component about half of the beam width, it is at least 50% of the initial magnitude. When the symmetry of a polychromatic beam is caustically destroyed, the decreasing of magnitude of the transversal components occurs much faster, at least by a factor 2 or 2.5, until it completely disappears in field of general type. Thank you for your attention.
Thank you for your presentation, and so the discussion is open for questions.
I have one question,
Yeah.
Igor.
Yeah.
I assume that the presentation you gave were based on computer simulation. Is that correct?
Yes.
Would it be possible, or is it very difficult to make real experiments to verify what you came up with?
This is not difficult for, at least for regular shift of spectral components, like here, for example, when we can analyze the diffraction from the white vortex by this screen. White vortex may be easily obtained, and we can see such shift of the corresponding spectral components, and we can estimate at least the intensity distribution.
Oh, thank you, Igor. Thank you for a good presentation.
Thank you.
Is there other question?
Yes, can I make a question?
Yeah.
Berkshire.
Igor, as far as I understood, you use polychromatic compositions, but what is the role of the degree of non-monochromaticity? Did you study the situation, how the situation depends on the spectral width of your polychromatic beams?
We have not exact dependence of them, but we have the paper where we consider the quasi-monochromatic approximation of this, I don't know exactly how our results changes under this condition.
Yes, I understand. It requires additional investigation.
Yeah.
Okay. Thank you.
Thank you. Other question? I have one question. Do you think about the application for optical tweezer? Do you think that it could be an advantage to use this kind of field and beam, and it could be, you can modify the force on the optical tweezer? Do you think about this kind of application?
I cannot say about the really polychromatic waves, but I see some perspective of use of optical tweezers, which are based on the superposition of 2 or 3 limited number of waves with different frequencies. At the previous conference, we shown the example of formation of optical trap by the green and red traps. And it seems me that it will be useful for capturing of the objects with different optical parameters, which are differs from one wavelength to other, and so on and so on. And the second reason is if we have the small difference between the frequencies, then the bit period may be very large, and during this period we have different situation in the formation of resulting angular momentum.
Okay, thank you.
So if there are no more questions, it would be a pleasure for me to introduce Professor Podolskiy from United States, who will talk about optical hypergratings for focusing vortex beams below the diffraction limit.
But I'm sorry, Professor Hanson, his talk is at 4 p.m. in Ukrainian time. Thus, we have a break.
Oh, good.
Because due to the difference in time, he is sleeping. And 1 hour we have a break.
That's fine. But I was so anxious to hear his presentation, so I couldn't wait.
Yes, we wait 1 hour.
So it's at 4 o'clock your time?
4 o'clock, yes. He is sleeping now in USA.
Good. Thank you.
Okay. Yes,
see you later.
We are waiting. Okay.
Bye-bye.
Thank you.
So we make the break now, if
Yes.
I understood it. Okay, thanks. And see you later.
All right, now.
It's a pleasure for me as chairman for this last session to welcome and say good morning to Professor Viktor Podolskiy, who will give a presentation on optical
I've changed the title, it's okay.
For diffraction limited resolution. So, Professor Podolskiy, we look forward to your presentation. Thank you.
Thank you. Can you hear me well?
You have 40 minutes.
Okay.
And we can hear you, yes.
Okay, let me share my screen then. So you should be able to see the PowerPoint. Let me start the presentation. Okay, so you should be able to see the presentation now.
Yeah, all is fine.
Yep.
It's fine. It's fine now, Professor Podolskiy.
Great, thank you. So I'll be talking about, I changed the title a little bit, as you can see. I'll be talking about hyperbolic metastructures for focusing light, and in particular vortex beam beyond the diffraction limit. So this is a collaboration between my group at UMass Lowell and the two students who have been working on this project for a couple of years are Evan Simmons, who is already graduated, and Jacob Lamountain, who is currently pushing on this research. On the experimental side, the mid-infrared experiments were done in a group of Dan Wasserman at University of Texas in Austin, and optical experiments and the structured light experiments were done at Duke University in the groups of in the group of Natalia Lechunitzer. So let me show you the outline of the talk. So I'll present first some information about vortex beam. I know that this is a conference with particular focus on the structured illumination and or structured light. So therefore, the introduction is going to be very short. I'll spend more time on talking about hyperbolic metamaterials and talk about dispersion, reflection, and refraction in these materials, and show you that these structures are unique in their ability to manage light beyond the free space diffraction limit. And then I'll talk about the particular application of hyperbolic materials in hypergratings and show you that these structures can be used to actually perform a high performance focusing of vortex beams. So let's talk a little bit about spin and angular momentum of light. I'm sure this was covered at this conference many times, but just so we're on the same page, light has spin that basically present in most of the plane waves. You can have either linear polarization of light, which represents spin being 0, or you can have circular polarization of light, and that gives you a spin of plus or minus 1, essentially. And in addition to that, one can structure optical beams so that they have not just spin or not only spin, but also optical angular momentum. Here, if you look at any plane of the light propagation, you will notice that the phase front is not homogeneous and exhibits a singularity. And then as you walk around the singularity, you would get some sort of non-zero phase shift that has to be a multiple of 2 pi. The key point here, and I will show it later on, is that at the singularity, your phase is not defined, so therefore the amplitude of light should be 0. And that presents key point or key challenge to focusing these lights, these sort of beams towards nanoscale. So why would you want these beams, and why would you want to focus them towards nanoscale? Again, knowing the nature of the conference, I'll not talk about applications on information capacity, on sensing, optomechanics, and imaging too much. I just want to point out that one of the exciting applications of a structured beam is their interaction with quantum or quantum-like particles, where having a non-zero transfer of angular momentum can enable emission into forbidden transitions. So this particular application of structured light requires nanoscale focusing, because you have to have ideally efficient interaction between your optical pulse and your quantum or quantum-like object. So how do we focus light? Well, we can do it, in experiments with lenses, but essentially what lenses do, they do Fourier transform, and they can adjust the phases of propagating beams. And so when these beams are large enough, as we see on this slide, we can represent them as wave packets with some well-defined and well-localized spectrum of angular momenta. We can adjust the phases of these plane waves, and then we can refocus light and basically recover our original focal spot. So the natural extension here is, well, let's start with the beams of light that are generated by smaller and smaller objects, and see if we can at least mathematically reverse the phases of the plane waves that constitute the resulting wave packet, and localize them into a smaller focal spot. So unfortunately, this is not what happens in reality. You may start with a small, well-localized optical packet. You would represent it as a set of plane waves, as you can see here. The spectrum, the wave number spectrum of this plane waves is going to be extremely broad. And as the spectrum propagates through the space, it will be sufficiently shrunk by what is called the diffraction. And so then if you try to focus the results in wave packet, you end up with a focal spot that's approximately half a wavelength in size. You can squeeze it, you can manipulate it, but more or less you get half a wavelength in the size of this wave packet. So this is the manifestation of diffraction limit of light that present essentially in any dielectric material. And that's what prevents us focusing light to the nanoscale and effectively interacting between the propagating optical beams and nanoscale objects. In the case of beams that represent a non-zero optical angular momentum, the situation is more dramatic and even much worse, because these beams are much wider in spatial domain, and then on top of it they have this hole in the middle. So even if you try focusing them, you basically focus in the empty space, and aligning and focusing at the same time becomes extremely challenging. There are a couple of approaches to focusing beams with optical angular momentum. These come from either plasmonic community or the so-called hyperlens community. But then aligning again your macroscopic beams that carry optical angular momentum with these more or less nanoscale structures becomes, again, a major challenge and prevents effective applications of this technology. So my goal in this talk is basically to show you that there is this field of hyperbolic materials and hyperbolic composites, and these structures seem to be ideal candidates for manipulating light at the diffraction limit, or actually beyond the diffraction. So first, let's talk about what hyperbolic materials are. Imagine for a second, or maybe for a couple of minutes, that you're given a homogeneous slab of material with huge anisotropy. It has a uniaxial anisotropic dielectric tensor, such that one component of this tensor is positive and one component of this tensor is negative. So if you draw a dispersion of a plane wave that propagates in such a material, it will follow a hyperbola. And you can see that it's drastically different from a conventional sphere that you end up with for an isotropic transparent material. So there are multiple interesting things that happen because of this hyperbola. The most, probably the interesting thing, or one of the most interesting things, is the refraction into these hyperbolic materials. You can see that if you want to calculate the direction of refracted beam, what you would do, you would say, this is my interface. I want the wave number that is perpendicular to this interface to be conserved. So, or sorry, a wave number along the interface to be conserved. So we fix the wave number, and then we'll look at which way the points in flux points in the incident wave and in the refracted beam. And you can see that you end up with negative refraction. So this negative refraction has been demonstrated in experiments in both infrared part of the spectrum and visible part of the spectrum. But more interestingly than that is the fact that this wide hyperbola essentially manages to postpone the onset of diffraction limit. And one of the ways to demonstrate that is to look at focusing of light in a conical waveguide-like structure. In structures with dielectric cores, these experience a cutoff, so the light that propagates towards a nanoscale tip would stop and reflect back exactly when the diameter of the waveguide becomes comparable to half a wavelength. In the waveguides with these hyperbolic cores, you can see mathematically there is no cutoff, and then you can do numerical simulations and show that, yes, indeed, the light would propagate all the way to the nanoscale tip of this device. So now that we hopefully see that these structures can support propagation of light in the very, very small spatial domains, let's look at how we can realize these structures. So there are several materials that actually exhibit hyperbolic dispersion throughout optical spectrum. There is a lot of them in far infrared spectral domain where you have phononic resonances. There are some in the UV part of the spectrum. But if you want to design a material for your particular wavelength of interest, you might want to consider composites. And so here I'd like to illustrate first the composites that operate at mid-infrared. So these are made by growing a large number of layers, semiconductor layers. Some of them are undoped. These are the gray layers here. And some of them are highly doped, so they behave like free electron plasma. And so by using semiconductor technology, one can adjust the doping, adjust the plasma frequency of these layers, and basically adjust the structure of this composite. So the typical thicknesses of the layers are of the order of 100 nanometers. The typical operating wavelength of this for these devices are of the order of 10 microns. And you can see there is a humongous scale separation between the vacuum wavelength and the layer thickness. And so because of that, we can represent this structure as an effective medium, and we can calculate both the permittivities of constituent materials, and this is the permittivity of these doped layers, and the effective permittivity of this multi-layer stack. You can see that this structure is anisotropic. The optical axis is perpendicular to layer surface. And basically, you have two components of permittivity tensor in the plane of the layers that are the same, and then the component that's perpendicular to a layer surfaces that's different. So I want to spend a couple of minutes discussing these different regimes. So permittivity of the doped layer as permittivity of any free electron plasma at small wavelength is positive, large frequencies, if you will. Then at the plasma frequency, somewhere here, that permittivity flips sign and becomes negative. And so basically that corresponds to transition of these layers, if they were very thick in size, transitioning from being transparent dielectric to being reflective metals. So, but the layers we have are very thin. They are much thinner than the corresponding skin depth size. And as a result, the composite as a whole does not become reflective. It actually becomes this uniaxial hyperbolic material. You can see the effective medium response on this side. And you can see that basically in-plane component of permittivity tensor, this blue line, remains positive. This material behaves exactly as the hyperbola picture that I showed you on the previous slide. And then in here, you can see that the component perpendicular to layers becomes negative. And so, yeah, to show you the dispersion, this is the hyperbola you've seen. It basically allows propagation of the whole spectrum of waves, and it can be used in particular to focus light to nanoscale. So as you increase the wavelength, the effective anisotropy flips. Material is still hyperbolic, but now it's reflective to the light that's incident at the normal. Only high index modes will propagate in these structures. And as you will see later on, this is the regime that's very advantageous to focusing beams with optical angular momentum. So to demonstrate that this is not just some sort of theoretical simulations, that this indeed can be observed in experiments, I want to show you the comparison of reflectivity and transmission of these multi-layer composites between the experimental results and theoretical predictions. You can see that the results match very well. And you can also see that these transitions from dielectric response to different hyperbolic regimes are associated with well-defined features in both transmission and in reflection here. And so this basically motivates this idea that you can use these multi-layer stacks as a very well-behaving, effective medium with hyperbolic response, at least at mid-infrared frequencies. So you can use them to build these waveguides that will guide light to nanoscale areas. And again, you can see a very good agreement between the experimental results of transmission through these structures and theoretical predictions of transmission through these structures for different diameters, top diameters of these, what we call them photonic funnels. And if you look at the transmission at the tip of the funnel at a particular wavelength, as a side of this diameter, you can see that our predictions and experimental results agree over multiple orders of magnitude. So we are pretty confident that these structures behave exactly as we want them to behave. So the original design of these funnels, they have these metallic cladding at the sides, and what that does, it basically keeps the waveguide modes propagating inside the structure without ever touching the boundary or leaking outside. But very interesting phenomenon occurs if we allow light to interact with this boundary. So let's look at that in a little bit more details. So now we have, again, our hyperbolic dispersion. This is the dispersion of light that is sort of outside the funnel, but now our light enters the interface node that is not perpendicular or not parallel to optical axis. So let's assume this is our interface, has some sort of angle with respect to optical axis, and let's analyze the reflection now of light within this structure. So to do that, we do exactly what we've done before for refraction. We rotate the structure so that our interface is horizontal. We say that our wave number should be conserved. And then the two arrows here, the two fat arrows, they represent the direction of Poynting flux of incident beam and reflected beam. And so you can see that depending on the dispersion, or in different words, depending on the wavelength of light that interacts with the same composite, you might have very interesting phenomena showing up. Your reflection is always anomalous. Your angle of reflection is not equal to your angle of incidence. So you can have weird combinations where your light enters the interface and then just continues on along the interface, or even have a negative reflection of light where your light hits the interface and then reflects back. And you can see that this there is a correspondence between these sort of dispersion curves and more or less hand-wavy arguments of which way the reflection should go, and full wave numerical simulations that represent solutions to Maxwell equations. What is interesting is this regime here, where your reflection basically causes light to propagate more or less along the interface. So in this particular case, what's happening, you can see that your light gets extremely enhanced. And this enhancement of local field, it's basically resulting from the epsilon near zero response that this particular beam feels. The interesting situation is that your permittivity tensor transforms as you rotate the reference frame, and in this reference frame, permittivity tensor is, or one of the components is very close to zero, so you end up with very strongly enhanced intensity of light. So that happens obviously in a funnel if you let it happen, and you can see, or you should see, the beam of light that's entering the structure not converted to the just converted to the waveguide modes, but if you let it propagate all the way to the interface, it will interact with the interface and just propagate towards the tip of the funnel. So we looked at how one can optimize the funnel performance with and without metallic core. The interesting, but now not surprising, take-home message is that you actually don't want metallic cladding on the structure. You increasing the intensity of light at the funnel tip by orders of magnitude by removing this metallic shell. You actually don't lose confinement because light keeps on propagating along the interface and stays, basically the confinement scale stays defined by the tip of the structure. So these are, as I already showed you some of the simulations, the expected intensity distribution of light within the structure, but then in all our setups and in all practical setups, the base of the funnel is about a wavelength of light or vacuum wavelength of light. And as a result, we just cannot fit the optical vortex in the structure, even though in ideal world, if you make it very large, you probably can utilize this setup to actually have focusing of optical vortices. So this type of structure is ideal for focusing non-structured beams of light. For structured beams of light, you need a slightly different setup, the one that I will talk about now. So before I show you the final setup, I want to talk about diffraction of light in these hyperbolic materials. And it's illustrated on these three pictures. The first setup, the one on the lower left, is the diffraction of light through a thin slit into isotropic dielectric medium. And you can see that your diffracted beam is actually a set of cylindrical waves that just propagate outside, away from the slit. So in contrast, in hyperbolic media, instead of these cylindrical beams, you have a set of hyperboloids that represent your phase fronts of the waves in these materials. Interestingly enough, depending on the hyperbolicity, whether your material is transparent for normal light or reflective for normal light, your beam, the diffracted beam, stays either within or outside what is called a critical cone. And I had an equation for this angle on previous slide. That's basically the tangent of this angle is given by the ratio of the permittivities of different components of permittivity tensor. So the existence of these critical cones has been pointed out a while back, dating probably back to late 50s at least, at the very least. But what was not realized is that you have these very high index modes that propagate very close to the cones. And basically what you can do with these waves, if you look at them in the wave number space, you can see that there is a lot of them, but you should be able to phase them in and try to manipulate them to achieve very sharp focal spots. So this is the proposal or motivation for the proposal. If you just start looking at the light transmitted through multiples of these slits, either rectangular or circular, you expect to see light beaming out in these cones and then interfere in these cones interfering with each other, coming up with a series of local maxima of light inside. So this already gives you a motivation that this looks very similar to conventional Fresnel zones. And in fact, if you take the approach behind the Fresnel zone design and add hyperbolic dispersion to it, you should be able to have subwavelength focus. The math is slightly different from the conventional Fresnel zone plate that is sort of done for far-field, isotropic, lossless materials. So in this case, you're dealing with very strongly anisotropic media. So this is the expression that gives you the boundaries of the individual Fresnel zones on top of the hyperbolic metamaterial. And if you open half of these Fresnel zones, you do end up with very nicely defined focal spots. Note that these are normalized to your operating wavelength, and you can see that they are very, very, very subwavelength. What I want to point out is that this particular design, the design for materials that are normally reflective to normally incident light, is ideally suited for optical angular momentum beams, because there is no light that's entering the structure in the middle, and all you need to do is to design the structure that's going to take the periphery of your optical beam and focus it down to the spot, either inside your system or at the boundary of your system, so you can interact this focal spot with a nanoscale object on the outside. So that's the motivation to design the hypergrating that will focus optical angular momentum beams with the only one fine print. So if we look at the materials that are available to us in the visible range, we will notice that, well, there are metals. They have plasmonic response that are shown here. They have negative permittivity. They behave exactly like those doped semiconductors, or vice versa. Doped semiconductors behave exactly like optical plasmonic metals. And then we do have dielectrics, and these are the structures, the dielectrics are not shown, and these are the structures that have indices of about 2 to 3 in the visible range. So we can build, effective medium response of these structures. These are the permittivities of the effective medium tensor. And again, you see the same scenario as you saw before. You have the one component of permittivity tensor slightly positive in the shorter wavelength, slightly negative in the larger wavelength. The second component of the permittivity tensor goes from negative to positive. So everything should work out fine, with the fine print that the thickness of the layer that we can fabricate in the visible regime is about 20 to 30 nanometers, meaning that the period of the two layers is going to be about 60 nanometers, and our operating wavelength is 500 nanometers. So you can see that, yes, there is some scale separation, but it's nowhere near the scale separation we see at mid-IR. So as a result, we expect to see corrections, and we expect to see modulation of our effective medium response in these materials, and would like to explore that. And so to explore that, to motivate this, I want to actually step not towards the correction, but all the way back to how do we think about modes and light propagating in these plasmonic metal dielectric composites. So if you have just one layer, obviously you don't have a metamaterial, but it's very easy to understand what's happening in one metallic layer that's surrounded by dielectric. So when you have one metallic layer, every interface of this layer would support a surface plasmon polariton mode. And as you make the layer thinner, thinner, and thinner, the two polaritons will start interaction with each other. So their indices will repulse, and you would get a symmetric and antisymmetric combination of these polaritons that are always called the long-range and short-range surface polariton, plasmon polaritons, and they're widely used in sensing and imaging communities. So now you add another thin metal layer to this structure, and obviously you bring two more plasmon polaritons. So now the four modes start repulsing from each other. And as you bring the two metal films closer together, what you notice is that one of these modes cuts off, and you end up with the 3 modes. One of them is still short range and long range polaritons, but the third mode behaves as a bulk waveguide mode, shown right here. And we call this bulk plasmon. And as you keep adding metallic layers to the structure, you keep adding these bulk plasmon modes. So now we see that these look interesting. You can clearly see them in experiments. They have very large effective indices. So the ones that are accessible in the optical range are the ones with indices of the order of 2 to 3. If you want to go higher, you probably have to start milling diamonds, and that's not very practical. But basically, a collection of these bulk plasmons start behaving exactly like the modes of the waveguides with uniaxial hyperbolic cores. As you keep adding layers, if you keep everything else the same, the indices of these modes converge to the predictions of effective medium theory. So those are the dashed lines on these plots. But you can see that for high index modes, and these are the modes we are interested in to get as much focusing as possible, the deviation between effective medium and the real indices is still significant. You can develop corrections to it that can be described through non-local effective medium theory, or you can just solve for them numerically. Either way, you can see that you have dispersion that is not exactly given by effective medium theory, but somewhat close to it. And you can use the dispersion of the actual multi-layer composite to design an analog of hypergrating. Basically, you follow the same approach you followed before. You choose a focal point somewhere inside your material. You calculate a phase lag that your mode would experience as you go from the optical axis of your device towards the periphery. The only thing you have to worry about is that the beam direction and your phase vector direction are different. Your beam goes in the direction of Poynting flux, which is given by the normal to this dispersion curve. And then the wave vector is the points of this curve. So you have to calculate the phase shift by your wave number, and you have to keep in mind that your modes go in the direction of Poynting flux. Now, as I said, this design is ideally suited to focus the optical angular momentum beams. And if we use our approach to simulate focusing of light by these diffractive structures, then we do see that we get very tight focusing for multiple angular momentum values. If 1, 2 are shown here, the diffractive structure itself is in this 1.5 micron range right here. And the intensity of light at the focal spot right on the tip of the device is shown on these plots here. So you can see that these focal spots are of the order of 1/5 of the free space wavelength of light. You can see that higher angular momentum have preserved their sort of donut shapes, and then the small angular momentum equals 1, it actually kind of bundles together and has very interesting phase structure at the tip of this device. So now we know how it's supposed to operate. Let's talk about how one go about fabricating this sort of device. And again, the fabrication part is done at the Duke University Licinitzis group. So we start with a transparent substrate. We deposit chromium that's going to be used as a hypergrating basis. So we drill with the focus ion beams, a beam degrading inside chromium. And then we can spin coat a PMMA layer on top. So the device at this step is shown right here. And what we noticed is that this device by itself, it's already can be used to generate small-ish beams with optical angular momentum. In fact, if you send in a circularly polarized plane wave to this device, it will convert that circularly polarized plane wave into a radially polarized m=1 vortex beam. So now we have the hypergrating set up. We remove the top PMMA layer and deposit metal dielectric multi-layers, and we use titanium oxide and silver as our dielectric and metal layers. You can see that this is the cross-section of the device. And so, as expected in the numerical simulations that I showed one slide ago, this is the focal spot, so that's where we expect to see focusing of our optical angular momentum light. So the only challenge now is to actually detect that focusing and characterize how tight the focal spot is. So we use isopolymers for this purpose. These are materials that react to the gradient of electric field, and they react to gradients of electric field by restructuring and changing their shape. So we deposited a layer of this isopolymer on top of our device, and the idea is that we shine the light from the bottom, and then we scan the top of the device to see whether or not we see any asymmetries in the distribution of this polymer. And of course, this is exactly what we see. So that's a focal spot of the device, the scanning electron microscope image of the setup, and you can see this isopolymer focusing and reshaping in the focal spot of our vortex beam. So the size of this structure is about 200 nanometers, and again, the operating wavelength of this device is approximately 550 nanometers. So this is deep subwavelength focusing of light with the optical momentum. So to summarize, I talked about hyperbolic materials, and I talked about manipulating light with these structures to focus both unstructured light with the photonic funnels. And there I showed that light can be focused down to about 200 or 300 nanometers, which is 1/25 of the operating wavelength. I then talked about the design approach, how to utilize hyperbolic materials to focus light with optical angular momentum. And we demonstrated experimental evidence of focusing optical angular momentum beams with deep subwavelength cross-section. These structures, just to give you one more point, they allow not only focusing of light to nanoscale, but also extraction of light from the nanoscale with comparable efficiency. And they can, as a result, be utilized for both focusing and outcoupling of light from nanoscale. Thank you. So that's the talk. Any questions are welcome.
I have a question. Hello. Do you hear me?
Yes, I can hear you.
Are the optical angular momentum beams the singular beams or not?
So my understanding that beams, whatever we call beams with optical angular momentum and singular beams and the structured beams, they are same family of solutions of Maxwell equations.
Okay.
So yes, the same thing.
The next questions. How does the topological charge or maybe phase structure of the incoming vortex beam influence to the design and performance of these hypergratings for achieving high resolution focusing?
So thank you. It's a very interesting question. So the design part does not seem to depend on optical charge. And I showed, let me scroll back, that the same design can focus both m=1 and m=2 beams. So you can see that so they both get focused with the same hypergrating. The structure of light and the focal spot, it's very interesting. So we're still looking at this one. and actually at the m=1 as well. What we see, at least from the preliminary simulations, is that these beams in the focal spot can be mapped to the skyrmion structures where the phase oscillates very fast along the plane of the structure, and then your angular dependence is basically given by the angular dependence of your incoming light. So if you send in m=1 light, you have m=1 dependence on the angular axis, but then you have strong modulation of polarization in this plane, in the radial direction.
Yes, thank you. And the second question is, are there limitations or challenges associated with using hypergratings to focus vortex beam below the diffraction limits?
Yes, of course, there are limitations. One that is often noticed whenever you deal with plasmonics is plasmonic losses. So you end up, your intensity of light ends up being limited by the losses of these structures. The efficiency is probably also related to that. To give you the sense of how much light you lose or how much light you can focus, you can see the intensity scale on this device, on this setup. So from this, you can roughly see that you can achieve intensities at the focal spot that are somewhat comparable, slightly lower than the intensity of your incoming beam. But obviously the size is much smaller, so the power-wise, you lose a lot of power in these structures. Probably they can be optimized. I don't know to what degree. That's one limitation. The second limitation is this breakdown of effective medium theory. Roughly, your focal spot is going to be equal to about the period of your structure, more or less. So those are the two main limitations.
Thank you.
We have time for more questions.
Yeah, sure. As I understand, it's Yuri. As I understand from your reports, you made enough different experimental setup with different grade shapes, yeah? With circle, maybe some other shapes, but you present only two results. Maybe you have some another shapes you investigate in your group, or you limitate only
that would
these
be
two
really
shapes?
interesting. Yeah, so the reason for circle is obvious. It's simple, right? It also simplifies numerics a lot when you have circle asymmetry, because basically, as you can see from this slide, you only can solve for sort of a cross-section of Maxwell equations. Yeah, more interesting shapes, I think, yes, that's a very good idea. We thought about it. I can't say we're thinking about it right now, but yeah, that's definitely in the plans.
In the future, yeah.
Yes.
And another one, what about diffraction efficiency of this structure? You measure these parameters or not, and what's the limitation of power from optical beams this structure have in your setup? From minimum to maximal energy that can through this structure can be used in maybe in medicine or in industry?
I don't know about medicine, because I don't think you need nanoscale setup in medicine. I think they are happy with like micron scale light, because all the like cells, they're large, they're not nanoscale. It gets you, honestly speaking, about the same intensity to the focal spot as the intensity of your incoming beam, but not the power. So the power is lost. But what it does get you, it gets you ability to effectively, very efficiently interact with objects at this focal spot. We looked a little bit at that, not in the optical angular momentum setup, but in the funnel setup. And so there we see Purcell factors of about 100, and more importantly, not just Purcell factors, but more importantly, we see about 10% of light being extracted from nanoscale all the way through the funnel to macro scale. And we hopefully gonna see similar efficiencies here. Just to give you a comparison, typically your extraction efficiency from nanoscale is literally below 1%. So if you go from below 1% to 10%, that gives you a much better ability to understand light-matter interaction.
Okay. Because we have some investigate with break gates of super focusing.
Yeah, we should definitely talk about that. I'd be happy to chat.
We still have time for yet another question if you have.
We try to make some.
Hello?
Yeah. Carry on.
Yeah, I think.
Did you finish your question?
Yes.
Do we
Thank
have
you very
more
much. Yes, we finished our this session. Second, yes, please. We finished today, and some announcement for tomorrow's session. We start tomorrow at 9 o'clock. We have 2 parallel sessions tomorrow, and the chairman of the first session will be Professor Bracelet and Professor Miglinski, and the parallel session, Professor Demchenko and Professor Halavka. And there are some changes in the program because we have a speech by Professor Wei Wang after the set presentation at 10:40 instead of this, which was skipped yesterday. Thus, we will meet tomorrow at 9 o'clock. Thank you very much. See you tomorrow.